All right, so yesterday we did the exponential functions explorations packet, and we talked about a couple of things. One, we graphed equations that looked kind of like this. 2 to the x, y equals 3 to the x, and y equals 0.75 to the x. Now, we noticed that when 2 to the x looks kind of like this, and 3 to the x looks similar, but just goes up a bit steeper. And we notice that 0.75 to the x comes in for landing. And we notice that all of these have a y-intercept of 1. And we notice that when this number was, which we talked about, when a was greater than 1, it was like the airplane was taking it off. And when this value was less than 1, so for example when it was between 0 and 1, the airplane was landing. So that was the general shape. And the equations look like this, and they're called exponential functions because the variable is in the exponent, and so it's a number raised to that exponent. Last, the big idea is that exponential functions grow by a given percentage. And that's a big idea because not all things grow in a linear fashion like we've been looking at. Sometimes they grow or shrink by a percentage. So these are the big ideas that I want you to get out of this. Now, here's the packet that I gave you today. And we'll kind of work through some parts on these first 2 pages, and then you'll be able to practice some. So, my name's Peter. There we go. So exponentials grow by a given percentage, and we find that percentage by dividing the nth term by the nth minus 1th term, or any term by the previous one. We'll look at this example in just a second, right? But let's talk about the general form. So yesterday we had a really simplified general form. The only thing that we're adding is this is our general form, where A is the start amount, which is the same thing as the y-intercept. Now all the ones we had yesterday had a y-intercept of 1, okay? But we're going to have a y-intercept that varies now, and we'll talk about how we find that. And B is the constant multiplier, or ratio. Now, so looking at this, given a table of values, how are we supposed to know that this is exponential? Well, you'll notice that the change from here to here is 4, and then from here to here this is 6, and from here to here it goes up by 9. Now, so we know that it's not linear because as n grows at a constant rate, as my input value grows at a constant rate, my output value grows different each time. Okay, so we know that it is not linear. Well, let's look at our general form over here. Okay, so this says y equals a times b to the n, right? If we put in 0 into this, we get a times b to the 0, right? Because we put 0 in for n right there. A times b to the 0, right? And we know that anything to the 0 power, whether it's a letter or whatever, equals 1. So all we have is a. Now knowing that, right, we know that we can find our start amount. We can always find our start amount by looking at the 0 term, okay? So in this case, my 0 term is 8. So that's actually my a if I write that equation. Y equals 8 times that. Because my start amount is always going to be whatever it is when n equals 0. Okay? Now, let's continue on. So now all of a sudden I put in 1 so if I put in 1 in my input, okay, then I get a times b to the first power, which is just a times b. Okay, and then my next one, a times b to the second, is the same thing as a times b times b. And put in 3, I get a times b to the third, which is a times b times b times b. Now, the big thing that I want you guys to notice, and you might need to put in these little division signs here, is that if I take one term, a times b, right, and divide it by the previous term, a, these cancel, and I'm left with my b term. And the same thing occurs here. My second term is a times b times b. I'll write that on top. And if I divide that by the previous term, in other words, this term here, then this a cancels, the b cancels, and I'm left with b. Once again, a times b times b times b, because that's my third term, is a times b times b, right? And I divide it by the term before, these all cancel, and I'm left with b. So by looking at this general term, I can see that if I take any term and divide it by the previous term, I will find that constant ratio, or my percent change. So let's look at this. So over here, if I take any term, I'm going to take 12, and I'm going to divide it by the previous term, 8. And that gives me 1.5. Let's take this one, 18, and I'm going to divide it by my previous term, 12, and I get 1.5. And I take 27, and I divide it by 18, the previous term, and I get 1.5. So my b in this instance is 1.5 to the x. So this is the equation that will create this pattern of numbers, where 8 is my y-intercept and 1.5 is my growth rate. Okay? Now 1.5 is greater than 1, so this is going to be taking off. So if I did a quick little sketch of this, right, I don't need to worry about this, right? So it's going to go through 8, and it's going to be an airplane taking off. So it's going to look something like that. And then on this end, remember that it's going to approach 0 but never quite reach it. Okay? So that's a quick sketch of that graph. Now, we talked about percent growth. So let's talk about this here. Okay? So oftentimes in books you'll see this, where the a is the same and the x is the same, but then they say that these are the same thing. So in other words, b equals 1 plus r, where a is the start and r is the percent change. Okay? Now if you think about that, then if I want to find that percent change, right, to solve for this, I'm just going to subtract 1 from both sides, and I'm going to get b minus 1 equals r. Now let's look at this in this case. So my b in this case is 1.5. And I subtract 1 from both sides. And my percent change is therefore 0.5, or 50%. So this equation, or this set of numbers, is growing by 50%. In other words, it's adding half each time. Okay? So given any value of a, we can find the percent change by finding the difference between b and 1. So in other words, to find r, we say b minus 1. For example, let's go look down here. Let's try and zoom in just a little bit. Okay. So for example, let's given this equation here, right? This is a 25% increase because here is my start amount, 5. Here is my b is 1.25. If I take 1.25 and subtract 1, that gives me 0.25, which is a 25% increase. Given this equation, here's my start amount, right? But this is my percent growth right here, is a 75% increase or my R value is 0.75. Okay, 75% increase. Let's see what we got on the back side here. Now it can go the other way too. So on the next side of the page, right, we have 100 plus 0.95. That's not a 2% decrease, that's a 5% decrease. Okay, I don't know why I have that there. Because if 1 plus R equals 0.95, if I solve for that, right, 1 plus R equals 0.95, if I subtract 1 from that, then I get R equals negative 0.05, or a 5% decrease. Okay. Here we have another equation. My start amount is 2 million. Here is my B value, right? And the difference between this and 1, so if 1 plus R equals 0.75, so if I subtract 1 from both sides, then I get my R value equals 0.75 minus 1 is negative 0.25, or a 25% decrease. Okay, 25% decrease. Moving on. So this is the big idea that I want you guys to mess around with or think about is, when we look at these equations, right, we're going to want to identify our start amount and we're going to want to identify our percent change. And our percent change is always the difference between this number, I should have a little X there, I should have an X there, between this number and 1. Okay. Now, other ways that we'll see these problems arise is if we get, we might be told what it is, right? So most automobiles depreciate as they get older. Suppose that an automobile that originally cost $14,000 depreciates by 20% each year. So let's write our general equation. Y equals, my start amount is this 14,000 times 1 plus R. Now it depreciates by 20%. So 20% equals 0.20, right? We move the decimal place over 2 places. And it depreciates, which means it goes down, so negative 0.2. Now, if we go back to our thing that is 1 plus R, okay, if this is my R is negative 0.2, so that would be 1 minus 0.2 to the X, which it might be simpler to rewrite like times 0.8 to the X. You can write it either way. These are equivalent, right? It's just down here I've done the math, and up here I can more easily see the percent change. Either way works, okay? Now let's look at this next question. Now let's use our equation, right? And actually, just for fun, I'm going to call it A of X for automobile, okay? So automobile of X equals 14,000 times 0.8x. Okay, let's put that in. It says after 2.5 years. So I'm going to put in 2.5 equals 14 times 0.8 to the 2.5. Calculator here. Now, how we do this in our calculator, for those of you guys who didn't catch this the other day, so I can turn this on, clear it out, right, is I'm just going to say 14,000 times 0.8, and then this is the to the key, this little shamrock right below the key, to the 2.5. So then my the value of my car after 2.5 years is $8,014.07. $8,014.07. And you can see this is a 20% grade. Now, when will the automobile be worth half its initial value? So what's half of its initial value? Well, half of this is 14 is 7, right? So let's see what we get here. Let's just, for right now, what we'll do is we'll just plug that into our calculator. So let's plug it into our calculator and take a look at it. So I'm going to go into y equals, and I'm going to say 14,000 times 0.8 to the x. Now I can go to my table and I can look and see when it's going to be worth. So you can see here's my start amount, 0 and 14,000. Now what I'm concerned about is when will it be equal half. So here at which is 7,000. So sometime during year 3 and 4. Now one of the fun things you can do with table set is you can actually, I can make my difference different. So let's start at 3 and let's go by 0.1. Okay, and once again table set is second table set. This is where it's going to start. This is 0.1. So I'm going to go to my table and you can see at 3 we already knew that. So right in here it actually equals 7,000. Okay. So I can say that my value, a of x, equals approximately 7,000 around February in 3 years. So a little bit into the year. All right, so now let's look at another problem. Let's look at another problem here. You invest $3,000 and are guaranteed 5% growth, right? So then once again, that 5% growth, right? That's the same thing as 0.05, right? And that's my R. So you can say, let's call it f of x equals 3,000 times 1 plus 0.05 to the x, or f of x equals 3,000 times 1.05 to the x. So there's my equation. This is a 5% growth, and you can tell because this is 5, the difference between this and 1 is 5, and I start at $3,000. How much money will you have at the end of 5 years? So then I'm going to say f of 5 equals 3,000 times 1.05 to the 5th. I'll put that in my calculator once again. 3,000 times 1.05 to the 5th. And so after 5 years, I will have 3,800. I will have that much money. So I will say f of 5 equals 3828.84. Okay. And when will my money double? So let's go ahead and I can plug that in. Y equals, put in my start amount, and times 1.05 to the x. Remember, this is your x button. 3,000 times 1.05 to the x. And once again, go to my table. Might want to reset my table set. So I'll go up by ones and go back to table. So I'm trying to find out when it doubles. So I want to see when it equals 6,000. So I'm going to go, and you can see that here is my input. Here's my output. I'm getting close. So between the 14th and 15th year, so after 14 years, my money will double. Okay. So anyway, what I want you guys to do for homework is look at these first, try and do this next page down through 1, 2, just do 1, 2, and 3. See what you got. Thanks a lot.